Welcome to me, almost ripping on my face, and to the second RavenDB conference. Couple of things to talk about. First of all, thank you for coming. If you look at your tables, you have these things over there. This is actually USB key. And these things gave me a heart attack about an hour ago because I plugged them in and they did not work. And we tested 5 of them and they did not work. And then I realized that I'm being stupid and I turned it over and plugged this the right way around, and then it actually did work. So please pay attention that this needs to go like this and not like this, and probably you have to do it 3 times to get the right thing properly, but that's USB and superpositions. This is important because in here you have the bits for RavenDB 3.5, and you have very early bits for RavenDB 4.0. And you have the bits there to run on Windows and Linux. In addition to that, we also threw in there a lot of the internal design documents that we have for both current and future things that we're doing. So that should allow you to get a view about what we're doing, why we're doing that, and how we are proceeding with things. Pay attention, those are internal design documents. They're not meant to be consumed outside, so maybe some of them wouldn't make a lot of sense. But I wanted to be as transparent as possible. I'm going to talk in this opening keynote about RavenDB 3.5. When we started working on 3.5, we got something very interesting. We actually started working on that in 2013, which is funny because RavenDB 3.0 was released in mid-late 2014. And I was sitting there and preparing this talk, and I started looking at the stats. So we have thousands of commits, and we have over 20 major features that I'm not going to cover all of them today. It's just too much. And the team size went from about 10 to more than 20 in the past 2 years. When we're talking about the big things for 3.5, then you have this list here: distributed work, operations, performance, and handling high-load situations. When we talk about 3.0, the major focus for 3.0 was things like operations, things like running on Voron, having the new studio, those sort of things. Here we said, okay, we already have a really good base. Let's see how we can push this forward. First thing that I want to talk about is distributed work. Now, tomorrow, Jonathan is going to do a whole talk just about how we can work with all of the new distributed features of RavenDB. So take into account what I'm going to do now is do a whirlwind tour of some of the new features in distributed work, and Jonathan will go in depth tomorrow. So the first thing that we need to talk about is the notion of clusters. What are clusters? In RavenDB 3.0, we have replication, and we have clusters of replications. Cluster of replications is effectively a set of servers that replicate to one another, and they all have the same information inside them. That has some issues with failover, because if a node fails over, then the clients need to fail over to a secondary server. Not all of them will choose the same server, and if the server that used to be the primary server comes back up, they will automatically go to that server. So what I'm doing now, I'm starting 3 new RavenDB servers. And now you can see that we have a new option. Not just create a new database, but go ahead and create a cluster. And I'm going to notice that I have port 8081 here, 8080, and 8082. In 8081, I'm going to create a cluster. And Now I have a cluster of just one server. Let's go ahead and add a new one. Here is 8082 and now 8080. And now you can see that we have 3 nodes. And you can see that we have a leader and 2 voting nodes. Why is this important? This is important because now all 3 nodes are able to make decisions together. Let me show you what this means. What this means is that I'm going to go here and create a new database. And this new database, I'm going to go to task and create some sample data. Now I'm going here, and this is a different database. One second. This is a different database server, and here all of my information. Right here for the taking. Notice that I didn't have to define replication. I didn't have to go and define the database on all of those servers. And more importantly, if I'm going to manage your server and look at the cluster configuration, all of them share the same cluster configuration. This leads to an interesting discovery. You can see that one of them is the leader. Now, let's, this is 8082. This is 8081. I'm just going to kill it. So now if I'm going to 8081, there is nothing here to answer my questions. So I'm going to refresh this. And maybe I shouldn't have tried to do this live demo now. Okay. So what's actually supposed to happen, I'm not really sure what this is doing. Let me. Oh yeah, I'm sorry. So I need to keep talking. So basically, I think there is 5 seconds, then there is some time to that. We did it specifically because we wanted to demo the, specifically because we wanted to demo the time that it takes you to do that. The default configuration is something in the order of 300 milliseconds, in which case a node goes down. In 1 second, we have the new node going up. Let's see if we're now up again. Apparently not. Oh, now we are. Great. Seriously? Thank you. Now you can see, sorry for that, the setting the timers for the demo means that this takes a lot longer, and I keep forgetting about this. So now you can see what happened. We have a node that is down. We have this node that is the new leader node, and this node is now just voting for that. I'm going to go ahead and start 2/Raven. I start the old server again. This is now running on port 8081. And notice what happened. This one came up. Now it's online again. It caught up with everything that happened in the meantime. This one is still the leader. So now 8082 is the leader for this cluster. Why is this important? This is important because that means that client will always try to talk to the leader. That means that if we have a failover in our servers, then again, on real configuration, within less than 1 second, we have a new leader selected, and clients are always talking to that. When the old server comes back again, then the new leader remains the leader. We don't have this jitter with old primary and new primary just fighting over who is going to talk to the clients. So that's much easier. It also means that we have much easier time just running in production, because we don't have this issue, and because honestly, failover is nice, but you will see those kind of features much more they mean much more when you're just doing routine operation, working with databases, migrating them, all of sort of things. Now, it's important to understand that while we're using the cluster for doing cluster-wide operations, the writing to the data and the replication between the nodes still happen as it used to. So we still have a multi-master system. And at the client level, you can select how you want to do things. You can say, okay, I want to go to write just to the leader. I want to read just from the leader. Or I want to read just from the, read from any node. I want to write just to the leader. I want to try to write to the leader, but if there is no leader, the replication level. And by default, if we go with, oh, I just want to write to the leader, then the chance of actually having conflict is much, much reduced because everyone is going to talk to the same server. Now, the next thing that we need to talk about is the notion of load balancing. So in RavenDB 3.0, we have load balancing for basically based on round robin. In RavenDB 3.5, we also have somewhere. Where is this? Let's see. Here we go. Okay. This one gets the biggest configuration option ever. But the basic idea is that we can do things like this. So I have a set of servers, and I define a minimal SLA time for getting a response for those servers. If the server is not responding fast enough for my queries, I'm going to stop sending requests to that. So over time, what happened is that I'm balancing based on the actual load on the servers to achieve my guaranteed SLA. So if I have a server that is being slow for some reason, for example, maybe you're just running a backup operation and all of the I/O bandwidth is currently held up because of that, RavenDB will automatically take that and start pushing the queries to other nodes, automatically on the fly. The end result is that we don't have to worry about finding the best servers. We just define, okay, this is what we want, and it just happens. The next thing that happened is we now have the ability to do more complex replication. In 3.0, what we did was, okay, you have all of this document here, all of them are going to the other side, and that's it. In 3.5, we now have the ability to, where are we? Yes, I need to do another one. So the screen size here is killing me. Here we go. So can anyone read this, by the way, on the back? Okay. So now I can say, you know what? I want only these 3 collections to be replicated. And then I'm done. And I can even take this further and say, you know what? When I'm sending the employee information, I don't want to send the email over the wire. Maybe I have some confidential data. Maybe I have stuff that I can't actually send to the other side. And I can just do that and modify things as we go along. I can also say, you know what? This record is too old. I just don't want to do that. So now I'm not going to send this employee over to the other node. So this feature is really nice, and it allows you to do some more interesting scenarios. By the way, I'm rushing through this, as I said, Jonathan is going to have a much more in-depth discussion on this tomorrow. Something that we found out is that the more that you have, the more features we have with replication, the harder it is to figure out why something isn't working the way it should. So we added this feature, and this feature we can basically say, okay, I have this document, and I have this destination. Is this going to be replicated to this other node? And if not, tell me why not. In many cases, maybe you have the filter replication that filtered that for some reason. But the admin might not know about that, and he'd look at the data and says, I don't know why it's not replicating. So that gives you all of that information very easily. Finally, this is relevant for those of you who have large clusters, talking about 5, 10, 20 nodes in a cluster. We made some significant work on reducing the network overhead when there are a large number of individual writes. So previously, what would happen is that all nodes would try to talk to all other nodes. Now we are much smarter about that, and we only talk on only talk when there's actually stuff that needs to be passed, and we know that in many cases, if this one talks to this one and this one doesn't necessarily have to talk to this one immediately. They can wait. And that's distributed work. Jonathan will continue that tomorrow. The next thing that we put a lot of focus on is around operations. And with operations, the major idea was simple. I want to make the life of someone who is managing a RavenDB cluster easier. So the first thing that we did, this was honestly for us, was to introduce the notion of the admin console. And the admin console is available from Manage Your Server. And here we go. And this looks like this. And the basic idea is that we give you the ability to execute JavaScript on the server, which isn't really new, but we also give you access to the full API that you have internally. So in this case, you want to say, okay, just give me the statistics for this database. And you get the raw statistics. There is an endpoint to do that. There is no issue with that. But here we can do something that you couldn't do any other way. So you can say, oh, I can see that my prefetching strategy is wrong, but I'm actually running in production, and changing that is going to require me to reboot the server, actually restart the server, but that's the same thing. I don't want to take the hit on my uptime. So now you have the ability to do things like that, which change things on the fly. In many cases, what we have found is that once we know where the problem is, fixing it is very easy. But the actual deployment of the fix can be extremely hard. Consider the scenario of something like RavenHQ. In RavenHQ, they have currently up to numbers of servers, and doing a rolling deployment can take a very long time. So if there is something that we can do and say, okay, we have this script, let's just do a for loop that pings all of the servers that we have and run this script and automatically fix this behavior, that's something that is very valuable. Notice, however, this gives you direct access to the server and direct access to the API, hence this operation thingy. It's extremely easy to do things there that would take down the whole server. So you have a lot of power, you also have a lot of responsibility here. And for the most part, this is not supposed to be something that to be used lightly. We added some stuff there as sample scripts, mostly so things like how do I change configuration on the fly is evident, but the expectation is most of the time, if you're touching that, you're very familiar with the internal RavenDB API, you're very familiar with what's going on internally and how it's going to affect things. In other words, it's there, it's available for use, let's not do that. The next thing that we talk about, we wanted to deal with operation was the notion of global configuration. And in many cases, we have users that run RavenDB servers to host a single database, because that's the application database. What we found that in many cases, we also have people who run many databases on the same server, one per application that uses RavenDB. And in that case, they have the same configuration across the board. But every time that they set up a new system, they have to have this checklist of stuff that they need to do. Oh, I need to define the replication, the backup, the version strategy, all of that. And here you can see all of the options that we have. We can say, okay, I have all of my servers needs to back up on a daily basis to this location. And once we have defined it in this place, it's being applied to all of the nodes, all of the database on this server. If we're using the clustering, then this can be applied to all of the nodes in the cluster automatically. So again, it's not changing the world. It's just meaning that a task that would take you 20, 30 minutes now take you 1. Another part of what we're doing is we actually have a dedicated support team of 3 or 4 guys who are the most knowledgeable about RavenDB in my office. And what they do, they accept customer issues of various kinds. And what we ended up seeing is that in many cases, the issues revolve around some sort of I/O. If you're running on Azure, for example, then the I/O pool is very shallow. That means that if you're issuing a request, it's going to take a lot of time until it comes back. Azure specifically compensates for that by being a very shallow pool that is also very wide. What does it mean? Every individual I/O request is going to take time, but you can issue a lot of parallel I/O requests that isn't going to impact a lot of your performance. So here are all of the different options that you see. And now you can see that in this case, we're doing a lot of index reads. That's what takes a lot of the I/O in this case. And we can narrow it down to, a lot of data reads from this specific index, or from this specific index on this specific database. Or I can see that a lot of my I/O is going into right into disk in this database. So if you have this issue of this noisy neighbor, now you can very quickly narrow down who is this noisy neighbor. In one particular case in RavenHQ, we had an escalated support call with hundreds of items in the disk queue length, right? Yeah, something like 300 to 500 size on the disk queue length. Just to give you some idea, 5 on the disk queue length is insane. And the reason there was that someone was doing a lot of, basically reading the entire database from scratch using streaming or subscription or something like that on every page load. So effectively they had, okay, I have this multiple gigabyte database. On every page load, I want to read this entire database from scratch. I don't actually know why they did that, but the idea here is that now you very quickly are able to isolate, okay, I know who is doing that. I know roughly what is the I/O operation. Okay, you're reading documents, you're writing indexes, stuff like that, and you can very easily narrow down and say, okay, now that I know what the problem is, I can decide what to do about it. Okay, along the same lines, I assume that any of you who is doing regular operation work in RavenDB is familiar with the notion of a request tracing. this is available here in Traffic Watch. And here we go. And you can configure the server to say, okay, I want to see all of the requests that is going on this server. So show me all of the requests to Northwind. And it will actually show you all of the requests to Northwind. The interesting thing about it is that now we also have these additional things. Once you do that, okay, this request took a while. This request took a while because, you see, 89 seconds, that's a lot of time, out of which 84 milliseconds, sorry, the number here is milliseconds, 84 seconds were spent in Lucene. And then I can look at this and says, we got 22 results out of 1.5 million. Now I can estimate why this happened. Probably the problem is that we have a very large query that we need to sort it. And sorting 1.5 million results is going to take some amount of time. Now we have something that we can do to fix that. In other cases, okay, you send me a query. The query that you sent to RavenDB was a 250 kilobyte in size. I'm sorry, parsing that much text is going to take me some time. Another issue. So RavenDB is built to be safe. Safe for use, safe for operations, for development. That's the whole concept of safe by default. That means that running certain operation on the server is just not going to work. For example, we don't allow you to do computation during query. We don't allow you to just grab all of the results. And that's really good for most things, but at some point I went to one of my guys and told him, can you tell me how many people do we have in Germany who bought licenses in Germany? He says, yeah, I can do that. I need to write the index to do that. It would take me, 30 minutes to give you those results. And the problem is that I don't want an index. I just need this one-time answer. So what we did, we added the ability to do data exploration. And data exploration basically gives me the following option. Select a collection and into X, order by X.count. Okay, so we don't have anyone with a duplicate name. Let's try first name. Maybe we have a duplicate here. No, nothing. But basically what you can see here is this link query. This link query is going to run over all of the data in the database. In this case, notice that we limit the number of documents and the time for executing this query. But obviously, you can raise that to reasonable limits based on what you're doing. And this basically just gives you the ability to run a query. This query is going to have a cost of ON. So however many documents you allow this query to run on, this is going to be the cost for that. And in the end, it's just going to give you the results. This is really nice if you want to do one-time stuff. You also have the ability to just export that directly to Excel and then send it to the business people to start doing some work on that. Another thing, and don't get too excited. I'm not sure if this demo will work. Okay, so this is us running on Ubuntu, and this is the RavenDB client for Python. And yes, for some reason, about half the time, there is an exception thrown because of some network issues between the virtual machine and the actual machine. So just fix that. And what you can see here is, I'm not sure if you can actually see that. 1 second. No. Okay, let me try it this way. Let's zoom out just a little bit. Okay, so everyone can read that? Yes. So now you can see we're opening a connection, opening a session, loading the document, and just start working with that. This is designed to be very similar to anyone who is both familiar with RavenDB and with Python. Primarily, this is meant for 2 cases. One of them, if you're actually working on a Python application, this has immediate relevance to you. The other scenario is when you have the operation teams and they need to do a whole bunch of stuff around that. So the idea here is this gives you an easy way to access RavenDB in a type-safe, dynamic, and easy manner. With all of the powers of RavenDB and all of everything behind it, so you don't have to do manual REST calls and things like that. So if you have some sort of an operational feature, things like that, throw it into a Python script, run it, and you're done. SNMP monitoring, which is probably one of the most boring topics one could talk about. I don't know if you notice, I intentionally designed this slide, presentation to be, okay, here is some exciting stuff that I can't talk about it because it takes too long, so Jonathan is going to do that. Now here, all of the boring stuff that are crucially important, but no one is excited about paying their taxes, right? You do that because you don't want to go to jail, but I'm not excited about that. So those are all of the taxes that we have to pay to be a really good product. So operation people love us, and they can support it in production, and everything is, but it's still not excited. Wait, the last part of the slide is really exciting because then I'm going to go into all of the nitty-gritty details about all of the evil things that we had to do to get things even more performant. But anyway, so SNMP is a simple network monitoring protocol, and it's effectively a standard way to monitor network servers and products. And what you can see here, this is actually a live instance that we have that monitor the live test server. And let's see if the network will hold. So if you go to zabbix.ravendb.net, you have guest access there, and you can start looking at things. And is this visible, Judah? No? Now? Okay. So I'm going to overview. And what you see here is that you have a whole bunch of information per database, per index on a database, all sorts of stuff like that that you can register yourself into and have it monitor. Now, I'm demoing that on Zabbix, and we have a template for Zabbix that you can make things much easier. But SNMP is supported on every single monitoring system that you have. So if you have a SCORM or OpenView or any of those sort of things, it's just going to work for you. Now, let's look at request for second on this server. And as you can see, it's not really being active. Most important feedback that we got from the mailing list and from discussion with customers is that there's too much instability in the versioning. So starting with 3.5, then when we release 3.5, this is going to be a frozen release. That means that there are going to be no new features on 3.5. We're only going to do bug fixes on that. We're going to still do some development on the 3.5 branch, but that's going to be separate. That's probably going to be called 3.6. And users are going to have the choice of, okay, I have this 3.5 release with bug fixes as they come along, or I have 3.6 with the new minor updates that we have, and I can choose which one to choose. And every time that we make a point release, so 3.5, 3.6, 3.7, we're going to freeze that, and we're going to move to the next minor version for any new features that we have. The idea here is, again, to increase stability. We have a problem with customers because, on the one hand, they want everything to be as stable as possible and have no changes that are not absolutely needed. On the other hand, we want to be able to iterate quickly, and if you have a bug fix, I want to get it to your hands as soon as possible. And in many cases, user request, I just need this little tiny extra team, and that will solve this big problem for us. So we think that this is going to allow us that we have the parallel work team going on. And I'm on time, and this is great because now we get into the fun stuff and the part where I'm really going to enjoy talking about. I don't know if you noticed, if you read my blog, you probably have seen that we have been doing a lot of performance work. And most of the things that we have been doing is analyzing production users of RavenDB nodes and discovering where the bottlenecks are. So the first thing that we discover is that there is this thread pool, and it sucks. I'm going to go into technical details. If you're not a .NET developers, this may be a bit obscure. There will be time for question in the end if you want to dig deep. By default, and what 3.0 is doing, we are using the global .NET thread pool to run indexing operations. That has a couple of interesting implications. Because we're using the same thread pool as everything else, this limits what we can do on the actual threads that we get, because this is not my thread. It's a thread that the system assigned to me for the short duration of operation, and that's it. The other problem is that if you have many databases on the same server, all of them share the same pool of threads. So now you have noisy neighbors that impact one another. If I have this big indexing process going on in this server, in this database, then this other server is being starved. The thread pool will introduce new threads into the pool over time, but this takes time. It also means that I'm indexing and handling requests on the same set of threads, all of which means that we have a lot of problems. So we created our own thread pool dedicated just for indexing work. That gives us a few really interesting features. To start with, we are now able to own those threads. They're only running indexing code. If we're only running indexing code, then we already know what type of code we're going to run on that, and we can optimize the work distribution accordingly. It means that if I have a high CPU load, I can say, you know what? I'm preferring to handle requests over indexing because I want to be as lively as possible. So I'm going to dynamically lower the priority of the indexing threads. And because those indexing threads only index indexing code, then we can get to the point where the OS is smart enough that they are dedicating this set of cores to the indexing and this set of code for request processing, and we have much better locality of reference with returns with the code that is executed. So we have overall much faster performance. We also did a lot of work around the allocation of work. So if we have a whole bunch of indexes running, and we have a few slow indexes. What we can do now, instead of wait for them to run, to complete the work, we can tell, okay, you take your time. All of the fast indexes are going to start running on their own, leaving you behind. And that gives us a lot more flexibility in the indexing process. So the fast indexes are going to run as fast as they can without waiting for the slow ones. We also have a lot more information available. So if there is any sort of issues, you can see, okay, this index is taking all of this time, and we have much better stats and monitoring around that. Lucene is a great full-text search engine, but it also has its share of issues. Some of those issues, we basically dug down and started looking at how we can improve things. Most of you are familiar with the notion of setting a field to be analyzed. Setting a field to be analyzed in Lucene takes 3 different steps. One of them is the tokenization process. One of them is the lowering the case of the characters. And one of them is stripping the possessive S, which sounds like low-level detail that you shouldn't care about, except that this meant that we would have to run over the string 3 times. What we end up doing is writing our own standard analyzer that has identical external behavior to the default Lucene one, but it does that in a single run over the string. So we reduce the amount of work that we do by 2/3. We also were able to reduce the number of managed allocation that we do in 3.5 significantly by doing things like that. Now, how many of you are debugging embedded RavenDB systems? Anyone? I know you do. Yeah. So the issue here is that when you're doing that, you might have encountered something very interesting. The look-ahead success exception. And the look-ahead success exception is thrown by the query parser Lucene is using because it uses exception as control flow. That has 2 interesting issues here. One of them is that for the most part, if you're debugging RavenDB code and you set the debugger to stop an exception, this is going to drive you crazy, absolutely crazy. The second, now, if you're running RavenDB test, which typically run on embedded RavenDB, that's very common. So you debug your test, and suddenly you have this look at success exception, and if you're successful, why this is the exception? Don't you expect to be successful? And the other issue here is that throwing exception is expensive. And throwing exception on the successful case, which is supposed to happen, means that you're going to throw a lot of exceptions. We have taken the time to rewrite the query parser that we use, and we rewrote it from scratch. Now, one of the reasons that we wanted to do that was to get rid of the exception handling. The second reason we want to do that because RavenDB isn't actually using the default Lucene syntax. We've added a whole bunch of things. For example, the in operation. Now, we added those as text manipulation on the query before and after we hand it to Lucene. Basically, a whole bunch of regexes. The problem with that is that when we profile our application, we saw that significant amount of time was actually dedicated to query parsing. If you remember in the operations, we have this thing. And this thing is here because in many cases, query parsing was an issue. Other way around. It was an issue because we would spend something like 3 to 7% of the query execution time just parsing the query. By rewriting our own, we have a much better system, both because we now have a query parser that natively understands the Lucene dialect that we use. We don't throw any exception, and it knows directly how to build the parse query that we need. Another thing that we did is try to work with, to reduce the amount of I/O that we generate as a result of using Lucene. And Lucene is using a set of files as the backing store, and it can generate a lot of I/O requests to the system. Most of the time, if you have small indexes, those I/O requests are actually going to be handled by the page cache on the system. The problem here is that while that's nice, that still means that you have to issue a syscall to the operating system to do that work. We have moved to using memory map indexes for all of our stuff. So now, not only do we get the benefit of the page cache from the operating system, we also have the ability to access the data directly without doing any extra syscalls, because the data is already mapped. Again, in the case that this happened, especially on Store.io, again, cloud system, Azure, and stuff like that, the difference of that is very, very significant, especially because we can also utilize features at the operating system level, such as read ahead and write behind, and those have significant impact on performance. Yes, so a lot of the things that drive us, a lot of things that impact the design of what we're doing are actually feedback from customers. Feedback from customers tends to happen in one of two areas. One, this doesn't work. Two, this is slow. And the problem is that in some cases, my reaction is going to be, yes, this is slow. You ask RavenDB to violate the laws of physics. And in some cases, my reaction is going to be, OK, let's actually violate the laws of physics. You have seen some of the things that we are doing with prefetching, with a memory map, with all sorts of heuristics around how we access the disk, how we avoid accessing the disk, all sorts of stuff like that. We have a bunch of features that try to balance things like how much I/O we can use, how much time we can use, how much memory we can use, and how much CPU we can use. So 4 different things that need to happen all at the same time, and 4 different aspects that we need to balance. For fun, all of that is dynamic because while we are making the decision, there may be a spike of traffic that's coming in. So we need to consider that a decision that we made at T1 would be immediately invalidated by the changing condition of the production system. We had a customer where when they rebooted their system, they would run a script that would load all of the databases into memory, basically access each of these databases. They have 500 databases per server, each database around 1 to 10 gigabytes, and they run the whole process in parallel. What this actually did was ask the I/O system, OK, now I need to read about 1 terabyte of data. I need to do it all randomly, all over the disk. And I need to do it now. What actually happened was that the I/O system says, OK, see you next year. So the complaint that we got was something in the order, RavenDB startup time is slow. What we actually ended up doing in some of those cases is literally put a limit. Because it is better to say, oh, I'm not going to do that, and reject the let's load this database, then load all of those databases at the same time, and basically kill the IO systems. The problem with doing those sort of things is double. One, we may hit a case where, maybe you have a system that can handle 1 terabyte of read in under 1 minute. But more importantly, we need to explain to the user why this happened. So in many cases, you will see that there are more endpoints available, and you can ask RavenDB a lot more, why have you made this decision? Why have you decided that you should reduce the batch size of your system? A common case is, okay, what I see is that indexing is slow. I'm going into the index stats, and I see that we are indexing in batches of 2,000 documents at a time. I would expect that to be 128,000 documents at a time. Why are you so slow? So now we can actually go and say, okay, why are you doing that? And we see, okay, we don't have enough memory on the system. Because we don't have enough memory, we can't load large batches. Or the IO system is being extremely slow, and instead of waiting for 3 minutes to load those documents, I would prefer to just load them as they go along and index them immediately. The number of consideration that we have to do there is extremely high. We also have better handling for many cases of memory utilization. That means that we are much better at detecting that, better at freeing a lot of the memory that we are holding for various reasons, caches, prefetching, indexing, replication, those sort of things. And we're also better at adapting to that. I mentioned that in indexing, we have a good way of going from learning from what the system is doing. So I see that I have a large number of requests going on. I'm going to dynamically lower the priority of the indexing so we can process requests. I see that I don't have a lot of requests going on, but I have a lot of indexing, so I'm going to shove them up again and give it higher priority so I can finish this quickly. And this is where I stop, and that's your time to ask questions. Yes?
Right now, a lot of cases or whatever.
Can you just raise your voice?
A lot of vendors, are prioritized like micro-bit.
One second.
How about you guys have a long term plan for a micro-based database?
111. Yeah. Can you? So the question here, just give it to whoever is talking. So the question here is, do we have plans to support running purely in memory?
Yeah, or something.
Yeah. We don't have a plan to do that. The reason we don't have a plan to do that because we already do that. You can run RavenDB in this mode, basically. That's the RAM, and it will run in pure in-memory mode for you. You can also select some databases to run in RAM. That will be it. Note, however, that if you do that, then this is purely in memory. We don't write anything to disk. Yes and no, because typically at that point what you do, you have one node that is actually writing to disk, and other nodes that are actually writing to memory and replicated to that node. So that's your persistent copy. However, for the most part, we haven't seen a real good use case for that. As long as you have enough memory on the machine, RavenDB is going to operate purely from memory. So you can actually see that if you open the a virtual memory map for a RavenDB process. And you can see that we mapped all of the data and all of the indexes into memory, and we operate directly from that. So in many cases, when you talk about, oh, I have a memory-only database, what they're actually doing, they are doing everything in memory and writing some sort of a log or something like that that is the persistent medium. And when you restart, they have to recreate the state from scratch. We went the other way around. We are writing everything to disk, and we are fully ACID across the board. But the access pattern that we do is almost purely in memory only. That's one of the things that we have done in 3.5 with indexing, for example, is completely eliminate all of the file error that we do, and everything that we do is actually just memory access directly. That means that as long as you have enough memory and the system isn't paging, you don't care. Yes. More question? Can you? Thank you.
I'll speak loudly back here.
Yeah.
Is there any plans for role-based access control to the admin consoles and the various management consoles?
So role-based access. So you already have only admins can do those sort of things. So if I'm going to here, when you're doing that, you can say, okay, you're admin, or you just read write, or you just read only. And if not admin, you can do certain operations. So in order to be eligible to run the admin console, you have to be an admin on the system database. Otherwise, it would refuse to do that for you.
Right, but I may want to execute certain functions that are not full admin as a, as an operational person, right?
Can you, one second, can you give him the mic?
So I may want to execute certain functions that are not necessarily administrative functions through that console as an operational person. Is there a plan to delegate or have some sort of role-based access control where I can limit what the person can do beyond just admin?
Inside the admin console, for example?
For example.
No.
Yeah.
No,
I mean, my intent is to provide an operational console, right, for ops people
yes.
who are not necessarily intimately familiar with the system, and I want to limit what they can do.
Yes. So what you do, you define an API key for that system, and you provide them here the set of things that that you can do inside the system, and they don't have access to the admin API key directly. They have access to your system, and you says, okay, Joe, you are allowed to, I trust you to not run this function during business hours, so you can do that. John, you have messed up, so you don't get the permissions to run this function, stuff like that. Effectively, what we do, we have the level of admins who can do everything. We have backup operators that can do backup restores, that's it. And we have regular users who can do normal operations. That's it. And I think you had a question? Yeah. 1 second, he's coming with the mic.
Yes, my question just relates to memory as well. Do you pre-allocate memory? I mean, it seems like, I've tried to give Raven, a set amount of memory before, and I'll just watch from, performance and not see it pre-allocate that memory as, like a SQL database or something would. And so that's the first question is there any plans to possibly pre-allocate memory? And then the second full question is, what is the rate at which you will put into memory? Like, is that per request? Is that when you dump to memory? And then how long does that stay inside of memory before it goes?
Okay, so that's a quite complex question to answer. Let me see if I can do it justice. So there are a couple of different things that's going on here. SQL Server does pre-allocation of memory, and then it just sits there. And it's effectively unused unless there is a pressure on the system. With RavenDB, we do something slightly different. We do pre-allocation of memory in the sense that we allocate buffers, and I'm going to give you an answer based on the native support for XML in SQL Server. That's been around for, what, 10, 15 years? No, 10 years, since 2005, if I remember correctly. I remember being extremely excited by being able to store XML data directly inside of SQL Server, and then being able to issue expat queries on that information. And leaving aside the ugliness of expat and XML, that's amazing. That's a really nice feature, until you realize that it has horrible performance implications. The problem here, and if you go and read the documentation today about how to handle XML data inside a SQL Server, what they're saying is, okay, you can define an XML index, but what they recommend you do, if you want to query on a particular field in that XML, you have an XML field in the table, leave that field to a real field in that table, and query on the table, not on the XML field. The reason behind that decision relates a lot to the way that you index unstructured data. Effectively, SQL Server is using a B-tree. That's not actually a B-tree, but it's a good line to handle most of the information. And B-tree over structured data is incredibly complex to handle, especially because that's something that is very foreign to the notion of relational database. Relational database has the notion of schema. I don't know if you know that, but schema makes the life of the database builder so much easier. I know what the size is. I know what I'm expected to do. No surprises. So much easier. I don't get people who gives me a single document that is 180 megabytes in size, and then they want to know why loading is slow. But that's actually that. You can see in PostgreSQL, they have JSON support for a while, including the ability to do some interesting queries on JSON, and that's not the same thing at all. You can store JSON, you can do some sort of queries on that, but indexing suffers, the ability to do aggregation on the information is very expensive. You have to babysit the database to what today is a stunning degree. It's funny, we go to a lot of conferences and we demo RavenDB. And something that I found to be incredibly frustrating for the past year and a half is that what we demo and the oh wow features that we have are all things that we had for the past 8 years. I don't get to demo any new feature because if you're not already using RavenDB, then something like, oh, you know what, let's just run a random query on this database, and let's see the query optimizer generate the appropriate index on the fly, taking into account previous history and all of what's going on. It's just crazy. And then you see, you know, even to the point where let's create an index on the live system. That's something that very few other systems do without locking the entire team. Now, in Oracle and SQL, you have the Enterprise Edition where you can define an index dynamically. To my knowledge, even if they have that, no one is actually using that because they're too scared of that. Because you don't do those sort of things on a live system. And we trust RavenDB a auto-tuning feature to that level that says, I'm not going to have the admin ask that. I'm just going to do that automatically. And we have experience now for running hundreds of thousands of RavenDB applications on millions of nodes, and to know that this actually works. And for the 98% of the cases, this does exactly what you want. Now, this is a feature that we had since 2011, maybe 2010. And since then, all we have done was all of the things that you saw about the IO metrics and the heuristic stuff like that, just improve on that. We do a replication. You saw me now set up a three-way cluster with replication between those three nodes with automatic failover and litter detection. And you saw me do that in 1 minute. Anyone here ever had to set up replication or something like SQL Server, Oracle, Mongo? Anyone? Any idea how much time it takes? Months. The typical number that I see from users is about 1 to 2 weeks to set up the simplest replication scenario using SQL. And I'm talking about, DBA that's certified, they know what they're doing. There's too many steps and too many things that can go wrong. It's not an issue of feature equality, because even if you put things on a comparison table, check, you're comparing apples to battleships. Yes, yes.
I have two questions.
Mhm.
First is, say 3.5 has the cluster, and is that the cluster will also replicate all the SQL replication scripts between those links?
And the answer is, to a certain degree, yes. You can define that in the global configuration here.
So that means all those regions you will try to write to one single SQL.
You can set it up this way. You can also override that configuration and not do that. So that's something that, replication happens automatically. This is something that you have to explicitly configure.
Okay,
And take into account that, if I remember correctly, if you can also do this so each of the nodes would replicate to their own node, to their own SQL Server database on the fly. So you define it once, and then it's based on the naming convention, it goes everywhere.
yes, because now we have 4 production regions, and only one of them is writing the data to the SQL.
Mm-hmm.
So now it's like in the cluster, I can configure only one region.
Yes, you could do that.
Yeah.
Yes, and that's the standard metrics for doing that. You can also, typically at that point, you would also say, okay, I have a 3 nodes cluster, and they are the voting members in the cluster, and they are the one that nodes are going to talk to. I also have a non-voting member in the cluster, and that just listen to whatever is going on, and that's my analytics operation that pushes that to a relation database, those sort of things.
And my second question is, 3.5 has partial replication for different collections.
Mm-hmm.
So do you have any plans that, and in the 3.0, we already can replicate all the indexes from region to region.
Mm-hmm.
But if you we can separate, we can partially replicate the collections, can we also partially replicate the index?
You partially replicating, you mean I don't want those indexes going over the wire.
Yeah, right.
That's not something that we consider. That certainly can be a feature.
Mm-hmm.
I forgot to put it on the slides. I'm sorry. There was, at some point, there was a schedule here for 3.5. I think I moved it to the 4.0 talk tomorrow. So the overall schedule for 3.5 is that we are now in beta.
Mm-hmm.
Probably in about 6 to 8 weeks, we're going to go to RTM, to RC, and a month after that to RTM. So if you still have features like that, this is the time to open an issue on that, and we can see if we can still push it to the 3.5 and not push it forward to 3.6.
Because we only replicate part of the
Mm-hmm.
to replicate that. So,
Yeah, that's a feature that needs to be discussed, yes. Okay, and that would be the last one. Okay, yes.
I wanted to ask if you can monitor I/O with a specific index.
That's possible. It's relatively easy for us to do it. We haven't done that yet in the UI that you saw, mostly because there hasn't been a lot of needs for that. And we want to make it simple to know who to blame. Once you're in a specific index, knowing which index it does, that is relatively easy. Once you know where the database is. Okay, guys, thank you. I think the next one is Judah. We'll take a 5-minute break and then come back.